In the last three videos, we've been largely talking about matter in terms of solids, liquids, and gases. We started with saying matter is composed of very small molecules which come together to form matter. They are solid because the intermolecular forces are strong, liquid if they are slightly weaker, and gas when they're relatively weak, and that kind of defines their shape and volume. Might have used the word density while explaining it. While it looks like something which is a common word which we use quite often, what does really density mean and what does it influence in terms of behavior of matter? So we said solid, the intermolecular forces are strong and therefore molecules are very close together. Let's take, for example, the same material so that you're talking about the same molecule all through. So whether it's a ice, which is a solid form of water, the liquid form of water, or the gaseous form of water, which is steam, let's take the same molecule of water. In its solid form, because the intermolecular forces are strong, the molecules are much closer to each other, which means we take a given volume of that solid water, which is ice, there will be a lot more molecules in that volume. Similarly, if it was water in that same volume, there will be slightly lesser number of molecules of water in that same volume, and similarly you would expect as you move towards a gas, that same amount of volume would have lesser number of molecules. Now each molecule of water had the same weight, which means that in that given volume, if there are more number of molecules, that volume of ice would weigh more than the volume of water than the volume of air. Therefore, if I introduce a concept of density, which is the amount of mass per unit volume of that material, I would say that the density of ice is higher than the density of water, which is higher than the density of steam, which is the gaseous form of the same molecule, which is H2O. So density then gives you a sense of how close the molecules are and therefore how much more weight they carry around it. Now density is an interesting concept because you can say that even if you were to compare solids, some solids would weigh lesser for the same volume than other solids. For example, if you see aircrafts are used and made out of a metal which is largely an alloy of aluminium as against steel, because steel is much more denser and therefore the same amount of material that you use, the total weight will be much more than for the aircraft that's made out of aluminium or aluminium-like light materials. In fact, we're talking about now composites, which are really plastics because their density is even lower. The reason we do this is because the density is lower, the same amount of volume is going to weigh lesser, and therefore it's useful for the function of flying, which is about taking things up. So coming from the concept of density, we have an interesting concept called flotation. I said it's easier to pick up the flight in the air because the air on the air floats, the aeroplane pretty much floats in air. Therefore, density fundamentally as a concept is the reason that things float. So things that are highly dense tend to sink, things that are less dense tend to float compared to the medium in which they are. So for example, if I have a glass of water and I put a piece of metal in, let's take a circular ball of metal, it would drop right in simply because the density of metal is so much higher than the density of water. If I put the amount of same volume of metal in terms of a different material like cork, which is like wood, it would float. Similarly, I could put different types of metals into water and kind of find that they float in different proportions. So we're going to put a piece of wood in, let's say, different liquids of different densities, let's say alcohol versus oil versus water, the flotation would be in line with the difference in densities of the two. So density, therefore, as a concept comes from packing molecules together and how quickly or how hard you bring molecules together. Of course, the weight of each molecule is built in into that calculation. But essentially, density as a figure, which can be measured as kilograms per meter cube, which is the mass per unit volume, or grams per centimeter cube, whether you're using this CGS units latter, or in the former case, you're using the SI units, kind of defines how much of material is there in a given volume, how much of material is packed into a given volume. You see the concept of density around you. Very often you see trucks moving on the road. If you, on the highway, you see trucks that are loaded tend to go very, very slow. That's because the truck is of a given volume, but when it's loaded, the mass is very, very high, and therefore kind of, the takes much more energy to pull. So the engine is working much harder to pull. Whereas when it is empty, it's only the empty weight of the container with nothing inside. So overall the mass is lower, and therefore it's easier to pull, because the material that was inside the truck when it was loaded was of much higher density than an empty truck which is now filled with air in some sense. So, it's much. So density then becomes a very interesting concept, which comes again from the fundamental makeup of matter, which decides whether it's solid, liquid, or gas. And then, of course, there's variation of even within solid, what are different materials we're talking about. So the molecular mass, the molecular weight, the molecular arrangement, how quickly they are packed, kind of lead to density. The simplest way to define for things around us is to use the word density, and therefore density becomes a very popular way of defining the structure of matter in terms of simply a mass per unit volume. And you can see that things like flotation are very, very easily explained for that. A lot of atmospheric conditions too, like the sea breeze and land breeze, are simply because on the ground, when it becomes hot, the air in contact with the earth becomes hot very, very fast. And when it becomes hot, it also becomes lighter, because density also depends on the temperature. Because like I said, if you heat, the molecules kind of agitated and tend to move apart, which means that there is lesser mass in the same volume, which means lower density. So this air rises up because it is lighter than the other air around it, and therefore cooler air comes in its place. In land breeze, it comes from the breeze flowing in the morning largely when the land heats up, and similarly in the evening it is the other way around. So the circulation of air, because of the changing of density, is typically referred to as land breeze or sea breeze, depending on the context. So I think largely, if you were to think simply from matter and how it is composed, it's very easy to talk about density as a concept and then talk about the effects of that density in terms of flotation and other sinking and so on and so forth. The other very, very often asked question, which tends to be confusing, is why does a ship made of iron float while a needle sinks? It's largely because of the density, not of the iron made out of the ship. A ship, as you can see, is very, very large, but it's also very, very hollow, because other than really the shape that holds it together, the inside of the ship is almost air or empty. And even if it's loaded, the shape is such that it's kind of blown up in a way that it occupies a very large volume for the same amount of mass. Therefore, the density is still much lower than that of a pin, which is a very, very compact, or needle, which is a very, very compact form of the metal, which is completely contained within that needle. So the volume is very small and all the mass is within that volume. So density of the needle is much higher than the density of the ship, while they're still made of the same material, which is really metal. So I think concepts like these come through simply starting from what matter is, how the molecules are arranged, and therefore what properties exist. Density being a very, very important property. I hope that helps you understand the link of matter in terms of its solids, liquids, and gas to its packaging density of molecules to actually the outward density that you see and measure. There are very many ways to measure density. The simplest being, if it's defined as mass per volume, you simply take the mass of the object and divide by the volume. For example, if it's a cube of aluminium, solid cube of aluminium, you simply weigh it, you get its mass in kg or grams, and then measure the dimensions length, breadth into height. For a cube it is similar, so it's side cubed, and then divide by the volume. So it's either kg per meter cube or gram per centimeter cube, depending on whatever units want to, and you kind of get the density. But what happens when it's an irregularly shaped body? It's easy to measure its mass because you simply put it on the pan of a weighing machine and you get its mass. But the volume is not so easy to determine because it's not a regular shape. One of the way to do it is simply immerse it into a liquid. And if there's completely filled to the brim, moment you immerse this solid object, irregular shaped object into the liquid will now overflow. Now, the amount of liquid that overflows in terms of volume will be same as the volume of the solid irregular body that you immersed into that liquid. So by measuring the volume with a measuring can or whatever, you get the volume of the solid, and therefore you do grams, which is the weight of the irregular solid, divided by the volume of water or volume of liquid it displaced, and you get its measure. The same way you can also measure density of a liquid. You take it in a jar whose volume is known. You measure the jar, so that you don't really want to measure the density of the jar, you want to measure the density of the liquid containing the jar. You fill it up, again weigh, and then you kind of subtract the masses so that you get only the weight of the liquid that contained in that jar, and divide by the volume of jar. And if you knew the density of a given liquid, let's say water, which is 1 gram per cc, you can also use this method to measure the density of another liquid. Because the volumes are going to be same if they're filled into the same jar, their masses are going to be different. So the ratio of the masses is kind of the ratio of the density. So you know water is 1, so you can determine what the density of the other liquid is going to be. All of this is very, very simple if you just think about and look at it in a structured way.